33 Raptor engines, fully loaded, ready to fire right now on Booster 20's launch mount. But here's the problem. The FAA's official slide said Flight 13 launches July 14th. SpaceX just confirmed July 15th. Someone got it wrong. And today, July 10th, sometime before the test window closes at 7 p.m. Central Time, the static fire, producing over 9,000 tons of thrust, will decide who's right and whether Starship finally fixes what went wrong on Flight 12. Let's break it down. Booster 20 is a super heavy rocket stage, 230 feet tall, carrying 33 Raptor 3 engines bolted into a single ring at its base. Today, July 10th, sometime within the 7 a.m. to 7 p.m. test window at Starbase, all 33 are expected to ignite together, producing more than 9,000 tons of thrust. To put that in perspective, that's more thrust in one instant than the entire Apollo program generated across its whole rocket family. Here's the part that sounds almost backwards. SpaceX isn't running this test to see if the engines can fire. They already know they can. Booster 19 fired all 33 engines successfully on Flight 12 just a few weeks ago. The problem wasn't ignition, it was what happened after. The booster failed to guide itself down for a controlled splashdown in the ocean. So why put Booster 20 through the exact same kind of test again if ignition already works? That question has a real answer, and it's the first piece of evidence in this story. Engineers aren't just watching whether the engines light up. They're watching how they behave under stress that's deliberately pushed close to the operational limit. Every Raptor engine carries hundreds of sensors, tracking chamber pressure, turbopump speed, and combustion stability thousands of times per second. A failure rarely looks like an explosion. More often, it's a tiny pressure fluctuation in one engine that falls out of sync with the other 32, and that tiny desync is exactly what caused problems after Flight 12. So here's the first data point in our case. Reliability, not raw power, is what's actually being tested today. Now, here's the second. The hardware supporting this test has quietly gone through its own transformation. The giant arms that catch Starship's booster, nicknamed the Chopsticks, used to run on a hydraulic actuation system. Hydraulics are powerful, but they shake. And when you're trying to catch a 230-foot-tall booster falling at speed, vibration is the enemy of precision. SpaceX has been replacing sections of that system with electric actuators, the same kind of shift you'd feel moving from an old mechanical elevator that jerks between floors to a modern one that glides, and they didn't just install the upgrade and hope for the best. On July 7th and 8th, engineers ran the arms through nearly 5 hours of independent testing, followed by another 3.5 hours testing the propellant quick disconnect system separately. None of these individual tests took very long. A traditional aerospace program might spread that same depth of verification across several weeks. SpaceX compressed it into a 2-day overnight campaign just ahead of today's static fire. That's data point number 2. Speed of iteration, not just raw engineering, is becoming the real competitive advantage here. The other rocket nobody's talking about. While Booster 20 gets ready, there's a second story happening at the same time that most coverage skips entirely, and it deepens the case even further. Ship 40, the upper stage that will sit on top of Booster 20, already completed its own static fire campaign. It rolled out, fired a single engine, rolled back, then rolled out again days later and fired all 6 engines in one test. From first rollout to completion of both campaigns, the whole process took 9.5 days. And here's the detail that matters most. During that exact window, a completely different vehicle, Ship 41, was running its own cryogenic testing in parallel on an overlapping schedule. Ask yourself how many aerospace programs on Earth can run 2 major test campaigns on 2 separate flight vehicles at the same time and still hit a 9.5-day turnaround on one of them. Right now, the honest answer is basically none. So we've got 3 pieces of evidence stacking on top of each other, engine reliability being tested to its limit, ground hardware upgraded and verified in hours instead of weeks, and 2 ships moving through testing in parallel without slowing each other down. Individually, each one is a technical detail. Together, they start to look like a pattern. And that pattern is exactly what's convincing people to bet real money on a rocket that hasn't even reached orbit yet. Why bet on a rocket that hasn't flown? Here's something that should sound strange the first time you hear it. Starship has not reached orbit. Flight 13 itself is still officially a suborbital mission. And yet, In just the past few days, one of the most detailed customer lists in the history of spaceflight has quietly assembled itself around this unproven vehicle. That's the paradox. Why would serious companies commit real money to a rocket that hasn't finished proving itself? Let's look at exactly who's doing it, and then we'll come back and explain why it actually makes sense. On July 8th, Tokyo-based iSpace announced it had purchased 500 kilograms of cargo capacity aboard Starship in a deal reportedly worth $50 million for a lunar mission targeted as early as 2030. Their CEO, Takeshi Hakamada, described high-capacity, low-cost lunar transport as essential infrastructure for building what he called a sustainable lunar economy. Here's what makes this specific company's bet worth pausing on. iSpace has already tried landing on the moon twice, both times using SpaceX's Falcon 9 as the launch vehicle in 2022 and again in 2025. Both missions successfully reached lunar orbit. Both crashed during landing. Despite that track record, iSpace is now committing to Starship, a vehicle that hasn't reached Earth orbit yet, for their next attempt. That's data point number 4, and it's the first sign this isn't an isolated deal. It's the start of a pattern. iSpace isn't alone. Astrolab has reserved capacity on a future Starship mission specifically to deliver a next-generation lunar rover, one designed around Starship's unusually large payload volume. The rover wouldn't make sense on a smaller rocket. It only exists because Starship's cargo capacity makes it physically possible. That's a different kind of bet than iSpace's. iSpace is trusting Starship's timeline. Astrolab is designing hardware that literally cannot fly on anything else. The circle of dependency is widening. Then there's Voyager Space. Their Starlab commercial space station is scheduled to launch aboard a single Starship flight no earlier than 2028 in a deal reportedly worth $90 million. Here's the comparison that makes this deal land. Traditional space stations get built piece by piece across multiple launches, sometimes over several years. The International Space Station took more than a decade and dozens of launches to assemble. Voyager is planning to deploy an entire orbital station in a single flight because Starship's cargo bay makes that possible in a way no other rocket on the planet can match. So now we've got 3 separate companies in 3 different industries: cargo transport, robotics, and space stations, all making commitments that only make sense if Starship succeeds. That's data point number 6, and it's enough to answer our earlier paradox. The bet finally makes sense. Here's the answer. These companies aren't betting on the rocket sitting on the pad today. They're betting on the trend line we just walked through. Reliability testing pushed to the limit. Ground hardware upgraded and verified in hours. 2 ships moving through testing in parallel. A 9.5-day turnaround that would take most competitors months. When you add all of that together, the bet stops looking reckless. It starts looking like a calculated read on execution speed, not blind faith in an unfinished machine. And that $140 million we mentioned at the start? That's just iSpace and Voyager's contracts alone, before you even count Astrolab's undisclosed deal. The circle keeps getting wider. Just when this story seems like it's entirely about commercial customers, a completely separate development plugs into the exact same pattern, from a direction almost nobody expected. On July 7th, the U.S. Space Force formally admitted 2 new companies into the National Security Space Launch Phase 3, Lane 1 contract vehicle, Relativity Space, and Impulse Space. Here's the detail that makes this genuinely surprising. Relativity Space's rocket, the Terran R, hasn't flown a single mission yet, not one. And they were still admitted into a pool of pre-qualified providers eligible to compete for future national security launch contracts. That tells you how urgently the Space Force wants to expand its list of options instead of staying dependent on a shrinking handful of established providers. Impulse Space is the piece that reveals something even bigger. They don't build rockets at all. They build orbital transfer vehicles, essentially tugboats for space, that grab a satellite after a rocket drops it off and carry it the rest of the way to its final orbit. Their admission means the Space Force isn't just buying rockets anymore. They're buying an entire transportation chain where one company launches and a different company handles final delivery. That's data point number 7, and it connects directly back to everything we just covered. The entire philosophy driving this shift, modular transportation, rapid iteration, reusability, is the exact model SpaceX pioneered with Falcon 9 and is now scaling up with Starship. The military isn't reacting to Starship directly. They're reacting to the operating philosophy Starship represents and restructuring an entire contract system around it. Here's the detail most viewers miss entirely. This new Lane 1 pool sits below a completely different tier called Lane 2, which remains reserved for the military's most demanding missions, the ones requiring the highest level of certification currently in existence. Lane 1 exists specifically so newer, faster-moving companies can prove themselves on lower-risk missions first, then graduate upward. In other words, the Space Force built an on-ramp specifically designed for companies that move at SpaceX's pace, instead of the traditional multi-year qualification process older contractors had to survive. That on-ramp didn't exist a few years ago. It exists now because SpaceX proved it was necessary. The other side of the story. Before we stack this evidence any higher, it's worth pausing to steelman the other side, because not everyone in the industry sees this as pure momentum. Flight 12's failed splashdown is exactly the kind of setback critics point to when they argue Starship's pace of iteration comes with real cost. A booster that fires all 33 engines correctly, but then fails to guide itself home, isn't a minor footnote. It's a reminder that speed and reliability don't automatically arrive together, no matter how many successful tests happen in between. Some aerospace engineers outside SpaceX have raised a fair question. If the company is compressing testing timelines to hit a monthly launch cadence, is there a risk that subtle problems get caught later than they should instead of earlier? That's a legitimate concern, and it deserves more than a dismissal. But here's where it runs into the evidence we've already covered. The nearly 5-hour Chopstick campaign, the 3.5-hour quick disconnect testing, the deliberate decision to push Raptor engines close to their operational limit during static fire rather than testing them gently, all of that suggests SpaceX isn't skipping verification to save time. They're compressing the calendar around it while keeping the testing itself just as rigorous, if not more so, than a traditional, slower-paced program would run. Whether that distinction holds up over the next several flights is still an open question, but it's the right question to be asking today, not a settled one. Let's stack everything we've covered so far, because seen individually, these are separate news items. Seen together, they're a single trend line. A booster on a launch mount today, about to prove 33 engines can survive their harshest test yet. Ground hardware upgraded and verified in hours instead of weeks. 2 ships moving through testing in parallel without slowing each other down. A lunar exploration company betting $50 million despite 2 previous landing failures. A robotics company designing hardware that only works on this one rocket. A space station company planning to skip a decade of incremental assembly in favor of a single flight. A military branch quietly restructuring its entire contracting system around the exact operating philosophy this rocket represents, and a genuine, still unresolved question about whether that pace comes with hidden risk, the same question Flight 12's failed splashdown put directly on the table. None of these 8 data points on their own would be a big story. Stacked together, they describe something much larger than a single test flight. They describe an entire industry recalibrating itself around one company's bet that speed of iteration can outpace traditional aerospace caution, while an honest question mark still hangs over whether that bet is fully paid off yet. What's really at stake today? So here's where all of this lands. 9,000 tons of thrust isn't just a number about engines. It's the load-bearing wall underneath every other commitment in this story. If Booster 20 performs the way SpaceX needs it to before that 7 p.m. test window closes today, Flight 13 stays on track for July 15th, Flight 14 gets closer to attempting orbit, and every one of those data points we just walked through starts looking less like a risky gamble and more like an early, well-timed bet. If it doesn't, every one of those commitments, the lunar cargo deal, the rover designed around a single rocket, the space station banking on one launch, the military's restructured contract system, all of it gets a lot more complicated at exactly the same time. That's the real story behind today's test, not just whether 33 engines can fire together, whether an entire, quietly assembled ecosystem of bets was built on solid ground, or on a rocket that still has to prove it deserves that trust. What do you think? Is betting $140 million on an unproven rocket a smart move, or one of the riskiest gambles in the history of commercial space? Let us know in the comments. That's the full data set on Flight 13. Thanks for watching. If this breakdown helped, like, share, comment your take, and subscribe to the Space Brief. More analysis is on your screen right now.